I'm sure that you're here for our next talk, which will be performed by Aksenov from Avito. We were practicing proper pronunciation a minute ago. I believe we achieved something. This man comes from a generation that believed that the Sphinx was a cat, and Kafka did write novels and not just store them in your backhand. Ladies and gentlemen, give you a warm welcome to Mr. Aksenov, who's here for you personally. Now's the time that you get on stage, my friend.
All right, man.
Now you have 40 minutes. That was your face before the after party.
That's most unfortunate. Oh, god damn it. Alright, so the world contents... God damn it. Заперся я в туалете. World Constants Tour 2022. I'm delivering this talk for like the 5th time in public, and before that about 2 or 3 times more in private. I'm the replacement speaker, so the majority of you must have come here for the Kafka talk, right? Is there anyone who came here for the Kafka talk? Perfect. Any more? All right, you will be delivered your take on the Kafka talk by the end of mine, because I have no idea how Kafka works internally. However, I'm kind of hoping that this is going to be the proper replacement for the Kafka performance talk, because I'm going to talk about the world constants which have to do with systems performance in general, and maybe, just maybe, knowing them and knowing about them will let you estimate any system performance, not just Kafka or anything else. Mind you, you won't be able to tweak any particular system without knowing its guts, ins and outs. However, this is some general info that does apply to pretty much everything there is, pretty much everything that runs on the planet, on the computers. Now there's the mandatory bio slide, and thinking about what to put on the bio slide, I realized that, of course, you don't care about my bio, you don't care about my education, upbringing, and of course, how many Franz Kafka novels I ever read. You do care, however, about the companies that I ever worked for or worked with. So I've compiled a list of a few companies. Some of them I've worked for, some of them I worked with, some of them are clickbaits, and I have no affiliation with whatsoever. You can pick an arbitrary number of companies I've worked with. Actually, the percentage is quite high. So there, pick a few, whatever names you like, and there's much more than 2. Back to the talk, and let's start backwards at the very end of the talk. Now, I am expecting this to be a rather bad talk, because I won't be able to squeeze everything that I would like to deliver in 30 or 40 minutes. However, I'm kind of hoping that at the very least it is going to incite some good thinking on your part, thinking about your particular system's performance, building blocks, and the constants that rule them all, if you will. So, there's the, what you call it, there's the offensive, if you will, E2, E4. So do you even know the required world constants, the constants required to estimate the performance of this or that system? And do you know what are the current values of those constants? How fast does your CPU work? How fast does your network work? What is your CPU capable of? What is your RAM capable of, RAM on your server, and so on and so forth? And last but not least, can you even count? Because most people, unfortunately, seem to not be able to. And 2 plus 2,700,000 something is going to be a problem for them. Hopefully, none of the mathematically illiterate are present in the room. If you are, well, I am sorry. Now, world constants, back to those. And of course, there are a bunch of constants which we all know by heart, even in IT, actually. So there is pi. It's approximately equal to 3.14 something, and it's the ratio, the typical ratio of failure of the time delta, right? So if a developer gives you an estimate of, I don't know, 1 week, then actually you should estimate for pi. it's going to be at least 5 weeks until the feature is delivered. And this is your typical developer, like junior developer or middle developer even. Not the senior developer, though. For seniors, the constant is E. So when the senior developer gives you your estimate, gives you his estimate, actually, or her, it's going to be off just as well. It's never going to hit the spot, but it's going to be less than pi. It's going to be approximately E, sometimes square of 2, but that doesn't relate. And of course, when your project manager comes running and asks you, so all right, which quarter are we delivering our project in? Finally, your typical reply is I don't know. So there's that. These are the constants we won't be talking about anymore, but rather their hardcore IT version. Initially, I hope, made popular by this guy, some principal dude at some Google company, ways back in 2010. So that was Jeff Dean of Google fame, and he delivered a brilliant talk like 12 years ago on VVWC or something like that, with a bunch of constants which pop every now and then, all the time ever since, which actually dive down really deep down to individual clocks and ticks within the CPU and level 1 cache performance, and all the way up to rather high-level things, meaning the time it takes the network packet to travel between two transcontinental data centers. However, I have a number of issues with this particular list. So, of course, that was then, this is now, 13 years or something like that have passed, and it's still a great start. Always was, probably will keep being a great start for a while more. But today, it's definitely somewhat off, because the computers actually kept progressing to some extent. The networks didn't. The time and the speed of light never changed. And of course, it's still going to take 150 millis or so to travel between the two data centers in Europe and in the US. But there's that. So I do have updates, and I do have, and that's the second beef I have with the previous slide, my very own additions, which I think let me estimate, well, my tasks better. And of course, a few benchmarks. So the three cornerstones on which pretty much all the performance in the world, well, software performance anyway, is based are rather simple, and we know them all by heart. Let me speak from my heart. So number one is CPU, of course. Number two is RAM. Number two is disk. And in this case, they are kind of sorted by the performance from the highest performance down to the slowest performance. Actually, I'm not taking the network into account because that's a wholly different story. At the same time, there's basically two major things that you want to care about, the latency and the bandwidth, and that should pretty much be it unless you're doing a DDoS service and you also care about esoteric stuff like packets per second, IRQs, and so on. So let's start easy, and easy is disk in this case, because just as network, it's really, really simple. What's disk? Actually, disk didn't change that much over the course of the last 12 years. It still reads in tiny units. I think back in 2010, sometimes the HDDs used to work with units of like half a kilobyte, 512 bytes. This is not the case anymore. The so-called physical sector on the disk is now pretty much always 4K, 4,000 something bytes. And you can manage to squeeze like 100 to a couple hundred random reads, taps, or actually random accesses, either reads or writes, out of your HDD still these days, and this constant holds. I mean, it was like 100 IOPS back in 2000 actually. It was at 100 at 2000 in 2010. It's still about 100, maybe 200 taps. So funnily enough, that never changes. However, with the advent of SSDs, the amount of the random I/O operations and even the bandwidth grew dramatically, as you, I hope, already read from the slide. So if back then, like 10 years ago, when you didn't have any access to any SSDs, or the prices were exorbitant, you had to maybe combine like 20 different disks into a single machine in order to squeeze out the measly 4,000 IOs per second out of that disk storage subsystem. Not anymore. Today you can buy one for like $50 and plug it into your laptop, and it's going to provide up to 50K IOPS in a single thread, 500,000 in when using 32 threads. That's crazy. The sheer amount of progress here is crazy. What was not even possible to achieve at the enterprise data center scale like 15 years ago is now possible using a customer-facing device. That's specs and benchmarks from Samsung Evo 970, available for, like I said, $50, maybe $100. So that's the simple part. But what I find interesting is that this actually already differs versus the initial scripture from 2010 in two things, in two major areas. Bullet number one is, the performance, it grew. Bullet number two is units. So Dean calculates everything in nanoseconds, maybe milliseconds if that's more convenient for you. That, in my opinion, is extremely not convenient to work with. And personally, I prefer thinking in terms of, all right, I can squeeze 100 megabytes per second out of my HDD, and I can squeeze maybe 2 to 4 gigs per second out of my SSD. And thinking of that in terms of 10 million nanoseconds per a single megabyte read is IMO, just way too many zeros, way too many redundant zeros to work with. However, your mileage may vary. Pick your poison and use whatever type of constant that you want to use. Either use the direct units or use the inverted and normalized units and compute everything in nanoseconds. Spoiler, I would not. Complicated. Moving on. So CPU. CPU is probably the most interesting beast of them all because there's just so much crazy machinery hidden within that CPU and doing all the kinds of magic which to the end user simply works. And the end user in this case is not the end user. The end user is us, whatever language we're writing about. Fun fact, actually, if we are even writing in assembly, we are not really writing in assembly because the CPU is breaking down the individual assembly operations into even tinier so-called mu operations, and then reordering them arbitrarily, and then executing them sometimes out of order, sometimes in order, and then. And that's just the tip of the iceberg. So there is a bunch of stuff, funny, crazy stuff going on within, which we really don't care about. What we do care about are just a bunch of general facts that, again, I kind of hope that everyone knows already, but let's do a refresher. So CPU is really, really interconnected really well with the RAM. It takes all it works with, both the code and data from RAM. That's the von Neumann architecture we're accustomed to for the last 70 years. And because RAM is actually slow, which we are going to discuss briefly, shortly, in about 7 minutes, CPU has to cache those reads. If you disable the cache on your CPU, it's going to slow down to a crawl. That was the case 20 years ago on the CPUs like 486 DX2. There was actually an option to disable the internal cache back then in those CPUs about 25 years ago. There is fortunately no such option anymore, and that's only reasonable because if for some reason we manage to disable the cache on the modern CPUs, to the observer they will basically halt. They will actually keep working, but the performance will be down the drain. So the caches are a must. And therefore, we must always take those caches into account when estimating or dissecting performance. Now, another thing that we should know, at the very least know that they exist, are the registers. They are tiny storage units, like basically tiny integers that the CPU works with. So your average run-of-the-mill Intel CPU exposes, I think, 16 registers on the 64-bit path, and that's where another fun thing kicks in. Actually, internally, CPUs have even the Intel CPUs which display, if you will, expose just 16 general-purpose registers to the end user, which in this case would be the assembly programmer. internally, they have like 128 registers, and they keep juggling them. When you write a bunch of instructions, they decode them and break them down into independent operations, and then squeeze them into the 128 internal registers. That's called register renaming for you. So all that magic happens pretty regularly, if you will, in clock ticks, which just tick, 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 and tick for a few billion times per second. Typically from, I don't know, 2.4 to 4.8, I think, is the biggest stock CPU clock on the planet at this point. And last but not least, they are pretty much all the time multi-core. Most of the time, you don't have just one core anymore, thankfully. You have lots of them. Oh, so all right, so boring. Everyone knows that. Now, oh, sorry. Now, just like I mentioned before, and we'll keep mentioning again and again and again, unfortunately, these are all these fun facts are just tips of the icebergs. There is an enormous amount of heavy machinery within the CPU. The caches, which are insanely complicated, the address decoding, which is like a five-layer pie these days, maybe even approaching the 6-layer pie, register renaming, MUOPs, out-of-order execution. I believe there's actually, in the most modern Intel CPUs, there's actually even a tiny neural net which tries to predict the outcome of this or that branch. At the very least, that's what someone told me over a beer, so that must be true. And of course, even the frequencies aren't guaranteed anymore. Even if your CPU says, all right, I can run at 3 gigahertz, it's actually going to run on an arbitrary frequency ranging from, I don't know, 800 megahertz to 4 gigahertz. So there, they are extremely complicated. And the bottom line, do not ever try to predict how this or that code is going to work. That actually worked 20 years ago. 20 years ago, you could just take a look at the disassembly and actually predict how many clock cycles is this code going to take. You could actually divide that by the clock frequency. And up to Pentium 3, I think, this was the last of its generation, up to Pentium 3, you could actually predict the performance of your code that way. Not anymore. And Pentium 3 itself was, I don't know, 20 years ago. Now, so always bench, bench, bench. But the rule of thumb, there are still some useful rules of thumb. And the major one, considering the CPUs here, except the bench, 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 don't even try to predict how it works, rule is that these days it's always 3 gigahertz. Whatever you do, your cell phone, oh crap, I forgot to put the timer on. So your mobile phone is going to be approximately 3 gigahertz. Anyway, even though it's a cell phone, it's ARM, not Intel, and in the data center, on laptop, on desktop, wherever we actually have, well, Intel, mostly. Some of them are AMD, like 10% of the market are on AMD, but, well, who cares? Anyway, and it's basically Intel architecture, Intel's implementation of AMD's architecture, actually, but whatever. Anyway, when working with a modern CPU, you can pretty much assume that it's going to be running at approximately 3 gigahertz. And that's a really fun fact. Another fun fact that I forgot to put on this slide, but I will put in right now, is that actually, when you do benchmarks on your laptop or on your desktop, you are probably going to get better results than in actual production on beefy, huge, extremely expensive server processors. Again, your desktop is going to be faster. And sometimes by a really significant margin, like not even 10% or 20%, but rather by 50%. The reason behind this, I believe, is that your consumer-grade CPU is going to be, well, low core, if you will. It's going to have, I don't know, 4, 8, maybe up to 20-something cores with the latest 12th generation of the Intel CPUs and the matching generation of the AMD ones. But the typical consumer-grade frequencies of those CPUs are higher because of the thermal package and because of the, well, cooling. And funny enough, the consumer-grade CPUs are going to be faster. That's pretty much a rule. Everything you see on the server is going to be slower. Moreover, the all-core frequencies that you see on the server almost never reach 3 gigahertz. Well, on Intel anyway. Of course, if you're running your Oracle database on a, reasonable Oracle/Sun server with just a couple thousand cores, every single one of which is certified to run at up to 5 gigahertz in stock configurations, then maybe, just maybe, the all-core turbo run is going to be at 3 gigahertz for you anyway. This is usually not the case with the Intel CPUs nor AMD CPUs. The all-core turbo frequency is, as far as I remember, almost never at 3 gigahertz. So for desktops, it's kind of the lower bound because they are going to overclock a single core and go much higher than that if you let them actually. So for benchmarks, it makes sense to disable that overdrive mode. For server, it's the other way around. If you're running at 2.8 in all-core mode, then you're actually lucky. Now, another fun fact that is the arithmetic operations, basic mathematical operations are extremely cheap these days. It takes just one tick, and actually even less than that, even less than one tick to add a couple numbers, subtract them, multiply them, but not divide them actually. But division is improving all the time just as well. Another fun fact, it's much faster to do a float division and perhaps convert the result into the integer than to actually perform an integer division on the modern CPUs. Another fun fact, the performance of that grew like 10 times over the course of the last 5 years from microarchitecture, from the Skylake 11th gen, I believe, microarchitecture. Now, bottom line, all that bullshit being said, how much operations is going this simple equation, evaluation really, going to take? C equals A plus B multiplied by 3. Do you think it's 2? It's actually not. Because actually that's 5. Because we have to load the A and B from memory, and that's going to take time, at the very least, one tick. Remember the very first line of the Dean slide, the L1 cache reference. That's also going to take time. It's going to be approximately one tick, sometimes even more than that. It's also going to take time to store that back into memory. So actually this tiny, super simple operation you're looking at with just 2 mathematical operations is, on one hand, extremely fast when it comes to actually adding and multiplying the numbers. But it hits a bottleneck when reading data from memory, just loading those variables from memory, if you have to do that, if they're not in registers already, and storing them back to memory. But then it gets worse, because who actually cares about the performance of this stuff? All right, it's so cheap these days, it's almost non-existent. What are our usual operations? And I believe this is really the punchline of the talk and the punchline of the takeout, and what I want to incite, the kind of thinking I want to incite in your heads. What are your personal usual suspects? What typically takes time in your particular program, microservice, database, whatever? What is that? Well, for me, because I'm a rather low-level guy, and even though I speak a number of languages fluently, of course, none of them being English, most of them being like, Python, Golang, PHP, Perl, version 4, of course, Bash, and so on and so forth. My language of choice these days is still C++, and that shows because my tools of the trade are the low-level operations like mallocs, qsorts, and hash finds, and so on. I would argue, though, that hash find basically hits everyone and bites everyone in the ass all the time, because in pretty much every single language you do have your own your very own hash table. It's actually going to be, in good cases, it's going to be implemented by the runtime authors of your language of choice manually, if you will. In the worst case, it's going to use the standard, de facto standard ordered map from from ordered map and C++ glibc, actually libstdc++, which is not really great in terms of performance. Now, these are my daily building blocks. I tried to figure out what could be other people's building blocks be. This is the best I could come up with. most of us work with the network stuff. Microservices shipping JSONs on a shovel from one backend to another backend, and then through a chain of backends to some kind of a front end. So we do work with networks all the time. We do work with databases all the time. We do parse JSON with vim and vigor in huge and extreme amounts. Sometimes we deserialize something from the network using gRPC and so on and so forth. Your typical building blocks may vary. And the point is, you really got to think about the performance of those individual building blocks at some point. So, like I said, my code is mostly C++, and the benchmarks I made about my building blocks reflect that. Case in point, actually fun stuff. I can estimate pretty high-level performance from, I don't know, how fast is ClickHouse going to run this query using just those building blocks. And the most fun part is the estimate is not going to be that off from the reality. Now, well, without a lot of further ado, the benchmarks, and these are current. I made those like maybe half a year ago in the summer of 2022 when I was working on version 0.3 of the stock. Malloc, how many allocations could you issue per second? And again, mind you, every time you create a new user instance in your Ruby script, you are almost inevitably, at least at some points, at least for some of the user classes, landing in malloc anyway. And the rule of thumb is approximately 1 million per second, except your performance may vary greatly, except for small enough allocations ranging from several bytes to several kilobytes. You are probably going to end up in that league. 1 million allocations per second, 1 million new objects created and or destroyed per second. It's not something you should do. I mean, if you're creating a million objects all the time, any given second, and destroying them immediately, you're not doing any useful work anyway. And the old good technique to create a pool of objects and work and reuse those objects still works in 2023. It's not automated really well, even though the modern allocators like gmalloc and tcmalloc try to do that. They not exactly fail. They do a great job. However, they are limited. They have limited control over the lifetime and scope of your objects. So there. Still works. Second building block. How fast is your sort, actually? What's the order of magnitude at the very least? Something that people rarely talk about. And I actually, before doing this benchmark, I actually tried to predict the performance of qsort using the n log n and whatever, and memory excesses plus CPU operations cost. I was solved by a factor of just 5, actually. So there. But the actual speed is not that bad. We are able to sort about 12 to 14 million integer values per second. Floats are most likely going to take about as much. This makes for a fun algorithmical homework, which is never going to help you in real world, almost never, but will let you shine when doing interviews for this or that company. Because that's pretty much the only time when you really have to engage the n log n rule or something like that. Of course, I don't know, once per year or maybe 2 times per year, you might need to estimate the performance of a system running at 2 billion objects using only a prototype with 20 million objects and estimate the additional delay caused by jumping up 2 orders of magnitude using the nonlinear models. But like I said, it happens 2 times a year. And of course, we all go to the interviews pretty much every day. We're programmers after all. So there's the homework for you. And the most complex task is going to be to find an implementation of radix sort and compare the standard quicksort with that. Hash finds. How many hash finds, how many hash lookups can you pull in 1 second? Again, this isn't really dependent on the language even, because in the end, you will end up running on this or that low-level C implementation anyway. And again, I benchmark. This time, actually, the estimates were not that off from reality. They were not 5x off. They were almost, on the spot, except for the worst implementations. And naturally, of course, the library implementation is always the worst one, at the very least in C++. In other languages, the hash table implementations are better than that. Unfortunately, there were some crappy standard decisions, standardization, if you will, decisions made way back when C++ from STL made it into the standard, and we suffer every day, every single day up to this point in time. The standard unordered map sucks. It's extremely slow. However, even the unordered map implementation will probably let you get away with up to 20 million lookups per second, a better optimized implementation, which ideally you would make yourself, but in the less ideal situation, you would borrow from Facebook or Google. They do have the corresponding libraries, lets you get to up to, I don't know, 50, 60 million lookups per second. Now, okay, that's all fun and games, so like memory allocations, sorts, subjects. What about the stuff we actually usually spend most of the time in our programs waiting for? Lux. And I wanted to benchmark the mutexes for some generation of this talk, that revision. Unfortunately, for this particular one, I didn't have the time, so we'll have to get away with the approximation to a mutex, the read-only version of the read-write lock, right? Because when we are using the read-write lock in the read-only mode, we're effectively grabbing a mutex for a short period of time, then incrementing the reader's counter, and then giving the mutex back. That's not ideal with regards to benchmarks, because there's almost zero contention, because the only protected operation under the hood, the only mutex protected operation is going to be basically counter increment, which is not usually the case in your program. You're doing much more than that under the mutex in your critical section. But, well, this will have to do. At the very least, this is the best case estimate of the performance. And 5 to 10 million locks a second, depending on how many readers we have competing for those logs. Oh, and this was taken, I believe, on a 98 core machine. That doesn't really affect the performance with regards to logs, but of course it does affect performance with regards to scheduling and having enough threads to run all those readers on. So hence the 128 readers as my cutoff point. The raw data is here, and quite naturally, when we have just one reader, in which case we don't even need to have any mutexes or read-write locks. But in some case, if we actually have just one reader, but we have to make our program multi-thread aware, we actually drop performance a lot. Mind you, the CPUs run at 3 gigahertz, right? So we are able to do like we must be able to do like 3 billion counter increments in one thread, on one core. If we protect that counter increment with just a single mutex, we're dropping our performance by a level of 100x down to 30 million a second. That's awful, but there we have it. And of course, it degrades greatly with the number of threads, because they begin to compete for the memory, for the counters, for the mutex itself, and the performance just drops. Still, a few million operations per second. That's good enough. Now, what if we had writers? Because most of the time, we actually have to write something to our data just as well. What if we use the read-write locks, which also do writes? And of course, and again, actually, as kind of expected, in this case, we can slow down our program down to a halt, essentially. If we have a few writers competing between themselves and competing with readers, and if we throw in enough readers, making the, well, writer's life worse. The raw data is as follows. And the fun thing about this part is that actually the sweet spot is achieved at, I don't know, 16 or 32 threads or something like that. That's kind of unexpected. I kind of expected the best performance spot to be at, well, the 2 writers at 0 readers, just the 2 writers competing for that lock, and no readers whatsoever. But curiously enough, the raw data shows that the actual sweet spot is at some balanced, at some, actually not really balanced, at some disbalanced place with as much as 32 readers, again, 96 core machine, 96 thread machine, sorry, 48 cores, and 2 writers competing for that. And but mind you, again, this is really the total operations per second, not writes. And the writes slow down severely. I don't think I have the raw data. No, unfortunately I don't. But I forgot to put that slide just as well. But that's counting. This is counting reads only. Sorry, this is accounting for reads just as well as writes. And this is the total operations per second. So the sweet spot with 6 million operations per second, as you can see, we carried out like 6 million operations per second. At the same time, it took 6 seconds, almost 6 seconds, 5 dot something, in order to complete 2 million writes. Because on this benchmark, I was doing up to 1 million operations within every single thread. And therefore, the write performance is much worse than that, as you, again, can unfortunately not see, but compute out of this. In this case, it's going to be a 300K per second or something like that. Now, the brief summary. So my building blocks, my building blocks, my benchmarks, and this is actually the stuff which is usually present at the back of my head and lets me estimate at the very least, very roughly, to the order of the magnitude, but still lets me estimate this or that program. So there, these are the the higher level additions to the initial world constants provided by Dean back then. And of course, funnily enough, there are a couple new kids on the block, the compression and decompression. And again, they changed a lot over the course of the last 20 years. And over the course of the last 5 years, I think, too, ZSTD, I would say, gained momentum. Anyway, to avoid boring you with details, because going into the details of the compression algorithm would require an additional 2-hour talk, which I, of course, also have with me on my laptop. Now, the typical compression performance is going to vary greatly depending on the trade-offs and bells and whistles and configuration options that you pass down to your compression library. But in the best case, you can expect maybe up to a gigabyte data being compressed per second. Basically, LZ4 at the fastest level, level 1, is maybe going to yield up to a gig of data being compressed per second. That's really the best case. Worst case scenario is going to be much more slower than that, but fortunately, it's not as slow as gzip. So the one takeout from this slide, throw away your gzip. If you're still using gzip to compress and decompress everything, just throw it away. Replace it with whatever. Replace it with ZSTD or replace it with LZ4. Actually, replace it with Snappy, with the Google compressor, which sucks compared to LZ4 and ZSTD. It's much, well, less performant in all these scenarios. However, even that is going to be better than gzip. And then again, this might affect your program. If your program is ClickHouse, which is nothing more than a glorified compressor that transforms your data into individual columns, chops them up in blocks of 64Ks, and then compresses them using, guess what, LZ4. That's essentially how ClickHouse works. Even if you don't embed any compression stuff that deeply in your program, but just use something to ship data across, or maybe compress your values cached in Redis, or compress something else that compress your JSONs that travel between microservices on your network, well, don't use gzip. Use LZ4 or ZSTD. So there. Now, almost everything that I just told you is a lie. Is a semi-lie, actually. Because the previous section was called CPU, and it's never CPU. All the additions and blocks on the previous slide, malloc, usort, all the way from malloc to decompress and compress, that's not just CPU. All right, there's a lot of CPU going on when we are running those operations. But the greatest beast of them all, and the one that affects the performance a lot, is RAM. And actually, I would argue that RAM even despite the fact that CPUs are so complicated and RAM chips seem so boring and well documented and with a lot of parameters, and when you're buying a module like that, you're going to have a data sheet which seems to be explaining every single thing that the memory chips are doing. The clocks are like, what, 15, 16, 24, 45. In this state, it's doing this. In that state, it's doing that. All right, it's so well documented, it must be easy, extremely easy, just with the disk to estimate the performance out of that RAM. The answer is no. I've tried several times when, well, working on different versions of this talk to try and figure out well, not really estimate, but predict the level of performance that I'm going to squeeze out of this or that memory chip using just the performance parameters of the chip. All right, so here I have the DDR3 memory clocked at this many cycles per something. And on the other hand, I have DDR4 25600 memory, which actually means the bandwidth. So if I have like DDR3 15,000 memory, that's actually easy. That means that the fastest bandwidth, the most bandwidth I can squeeze out of this chip is 15 gigabytes per second. Not more, not less. If I'm doing huge linear reads out of that chip, I should be getting 15,000 megabytes per second, 15 gigabytes per second. That's the specification, and it never works. I've tried a lot of benchmarks, and the funniest part about it is that, all right, so I'm running on a benchmark on a DDI4 server, which is supposed to yield 25 gigabytes per second, and I'm getting 22. That's all right, that's as expected, right? However, when you buy, I don't know, well, a mini car, and suddenly it accelerates to 500 kilometers per second, you're doing something wrong, or the car is doing something wrong. But that's exactly the results I was getting with the DDR3 memory, which, to the specification, the chips must be yielding 15 gigs. I'm actually getting 17. Repeated benchmarks, no room for error, 3 reviewers, nope, 17 gigs per second, that's it. That's why I called the RAM the 17th circle of hell. It's extremely complicated to predict its performance, but bad news and good news. So even though all the benchmarks before are semi-lie because they already combine CPU plus RAM, well, they're still valid, right? They're benchmarks. I've actually benchmarked how many hash lookups, read-write logs, allocations, and so on I could do per second. And those numbers stand. Now, you can't predict them based on CPU only. You have to take RAM into account. You can't really build a theoretical model. The point is, you really can't build a theoretical model in most cases, which is going to predict something, even something is as simple as sorting the integers. That's weird. However, you can still predict the performance of hash find, actually. But that's a different story. Now, there are good news. For the last, I don't know, 5 to 10 years, we're all used to ML. And every time the human brain is not up to the task, we turn to ML. And we can use machine learning in this case just as well. So, all right, we have something extremely complicated. Curiously, it's something that we didn't think would be so complicated. It's RAM, it's basic RAM chips. But we just can't predict them performance. We just can't build a proper model. What do? Well, we turn to ML. And ML, in this case, is just benchmarks. And if you do your benchmarks right, and doing these benchmarks, doing benchmarks which even touch RAM, which are essentially all benchmarks, you must account for cache. The rule of thumb here is really simple. You just have to throw enough data at your benchmark. You have to account for the fact that the cache line in the CPU is going to be 64 bytes. You have to account for the fact that the L2 cache is 2 to 4 megabytes per core. You have to account for the fact that L3 cache never actually works, and you can't even tell if it's present in your CPU or not. The benchmarks are all the same, but it all boils down to throw 32 megabytes of data into your benchmark, or a gigabyte, which is not much anyway, and your benchmarks are going to be A-OK with regards to caching, because that's just enough data to wipe out all the caches at all the levels. to flush the L1 and L2 and even L3 caches down the toilet and sometimes, and get the actual sustained performance you are going to be actually seeing in prod. So ML, benchmarks and statistics, aka the simplest form of ML ever. And even though RAM chips are extremely complicated to predict, they are easy to benchmark. And curiously enough, I've benchmarked like 4 different generations of machines, of CPUs and RAM chips, and got pretty much the same result out of every single one of them. I'm benchmarking 10-year-old desktop. I'm getting, well, 40 million random reads per second from memory and about 15 gigs of transfer. I'm benchmarking a modern server, which we just bought, which is, well, last generation. I'm getting 40 to 50 million random reads per second and maybe 17 gigs of transfer, but that's the ballpark is still the same. We can still count on memory being able to do approximately 15 gigs per second, except if you're running your benchmark on the Apple laptop, the M1 Apple laptop, which literally changes everything. All these benchmarks just jump up 3x if we switch to that. But that's not really because of the M1 chip, I think, but because of the DDR5 memory. And yes, the benchmarks are going to jump really, literally 3x. I was amazed. I thought we made a mistake and ran the benchmark with a tiny data set, like 20 gigs instead of, 20 megs instead of 4 gigs. Nope, that was not the case. They are that fast. And nope, you can't get that level of performance on your server. Not just yet, anyway. I'm kind of hoping that in a couple of years, we will start seeing servers that perform just as well. So that's about the size of it. What have we learned, or at least noticed? So in pretty much any system, there are multiple components. The usual suspects, the boring ones. The CPU, the RAM, and the disk. There are a few constants which let you estimate the performance of, well, pretty much everything using that. There are older versions, the fundamental scripture delivered in 2010. There is my take on those constants. And you can, and I think sometimes, at the very least once a year, once per 3 years, you should try to think about your particular building blocks. Who cares about my malloc if what you usually do is JSON parse in your language of choice? Benchmark that sometimes. That will really help you estimate the performance. And you can estimate system performance in a really precise fashion using that. But unfortunately, to delve into examples, I need 2 more hours, and I just don't have the time for that because, well, we have the timeout. And that's about the size of it. So there, questions, comments, concerns, homework, your own benchmarks, that would be most appreciated. If you have any of that, well, you can use any of the methods to contact either myself or the organizers. And of course, for those who are taking pictures during the entire majority of the talk, the slides will be available. These are the original constants. These are the my constants, and this is the sample that I don't have the required 2 hours to dissect. That's it.
Any questions? Thank you, Andrei. That was philosophical and entertaining, as usual.
And boring.
No, you're not boring. You're different.
Which doesn't mean good, right? The fact that you're unique doesn't mean that you're useful.
Yes, you are. But I don't have another hour to explain it.
Yes,
okay,
yeah. At the very least, I was able to fill the time.
So you told about the division on the Intel CPUs and that it is fast, but as far as I'm aware, ARM CPUs are missing fast division. So do you account on that in some of your benchmarks, or just like how do you plan for it?
You would have to account for that if you're doing a lot of math and if you're doing a lot of divisions, which actually is surprisingly rare. And frankly speaking, I don't have the slightest idea on the specific performance of individual operations on ARM. Actually, I don't even care, curiously enough. I don't even do enough integer divisions on Intel to care much about those. Surprisingly, that's a rare enough operation. Surprisingly, mostly you care about the floating point performance. But yes, you are correct. If you're doing a lot of that, you would have to account for that, sure.
Thank you. We have a question over there. Yes.
Hello. Can you provide one example from real production system when this knowledge helped you significantly, not in benchmarks?
I would say that they help me every day, except I infer the models all the time. I mean, I see something, I see a query which runs at, I don't know, 100 queries per second. And immediately a built-in trigger pops up, a tiny little window pops up in my field of vision saying, what the actual hell? This query is not that complicated. It's doing maybe, I don't know, 5 million divisions, 2 million random accesses, and a few of hash lookups. Why the hell is it so slow? 100 queries per second, 10 milliseconds per query. That's a lot. And if and when that kind of warning pops up, I'm usually able to optimize the query in question tenfold. So yes and no. I can't really provide any live example of doing that in prod, because that's usually happening in development for me, not in prod, and that's usually happening as I go. I just don't write down those examples. I've made an example of trying to estimate what kind of performance a simple SQL query is going to take, and that's an interesting journey for the interested, but really that's another hour and we should take it outside.
Okay, great.
There will be some time that you can spend at the discussion zone. Yes, let's take the final question, please.
Okay. You mentioned that C++ to unordered map is slow. Do you know if there are some objective reasons for that, or are just stud library writers
Of course
hopeless?
they are, but that's a question of chicken and egg. Basically, it's slow because it provides a bunch of guarantees that if you ever add an object into that, it's never going to move in memory. And that's a strong guarantee which you never need, actually. If you make a simple map with string keys and integer values, so the kind of maps that we make every single day, if we do that, you don't really care where exactly in the memory the key resides and the value resides. You only care about the fact that you are able to really quickly look up that value by that key, increment the counter, read it, and so on and so forth. Unfortunately, an ordered map provides much stronger guarantees than that. It does guarantee that the value won't move. I'm less sure about the key. But in order to provide those guarantees, it needs to sacrifice the performance and implement itself in a different way, in a slower way. And I think the flat maps are slowly making it into the standard. I don't think they definitely haven't made their way into a widely deployed standard just yet. That would be C++ 17. Flat maps are just not there yet. They are getting there, but it's taking a lot of time.
Thank you, Andrei. You need to pick whose question gets ahead.
I'd say the production examples one. That's exactly what I'm inciting everything to do, to work with their production issues. So someone over there.
If you could wave to the helpers. Whose question was that? Or did that person leave already? Okay, the guy left. 1 or 3 then.
Sorry, that's complicated. I kind of locked on the.
So 1 or 3, pick a number.
Yeah, let's do with the most recent one, the map one. Then. Yep.
Okay, so
that's easy.
You get a prize for a good question.
Yeah, so winning is easy when you're the only person competing. Right?
Yes. Please make sure you rate the talk. We do need feedback. Andrei, thank you very much. That was good.